In this video, we're going to look at begin looking at section 2.2, which is called the derivative at a point. Okay. This section is in the context of section 1.8 and 2.1. So in 2.1, we had learned about what was called the average rate of change, the average rate of change of a function f of x from x is equal to a to x is equal to b. You can look at previous videos on that. Essentially, the formula is that we are looking at f of b minus f of a divided by b minus a. Okay, so in the context of the example that you're seeing over here, over on the right of the screen, you are seeing the function f of x is equal to x squared. Okay, I've created a table of values for it. Probably do what you would do. You would put in some x values into this function, and let's see, I'm picking, say, negative 1.5. Negative 0.5 and 0, for example, and when you plug those in, you'll get 2.25, 1, negative 1.5, 0.5, you'll get 0.25, okay, and when you put in 0, you get 0, of course, okay, and let's see, then when you put in 1 and 1.5, you can see the values over here. You'll get 1 and 2.25. Okay, so for example, the average rate of change of this function f of x is equal to x squared from x is equal to 1.5 to x is equal to 1, right, is the function evaluated at 1.5 minus the function evaluated at 1, pretty simple to do, over 1.5 minus 1. So a little bit on terminology before you notice what we're looking at here. Okay, in the sections that we're going to be looking at, this is what we were calling our delta x value. Delta x is how the values of x are spaced out. You will often see the book refer to that as the letter h. So h is the spacing of the x values. Okay, and then when you compute this number, the average rate of change from 1.5 to 1, from 1 to 1.5, that number should come out to be 2.5. Okay, should be this number in the table right here, from 1 to 1.5. So it should be the 2.5. Okay. Now please keep in mind what we have just done in that problem. Here you can see a plot of the function. I've just plotted two of these data points, plotted all the data points there. You know that if you increase the spacing, you can get a better picture of what this function looks like. You plot, some more points, and you'll see that this is going to make the parabola. So clearly, you know how to plot data points and connect the lines. So what we just computed with the average rate of change. What we just computed with the average rate of change is the slope of the line between those two blue points right there. So when you plot the function at a, in this case 1, and b is equal to 1.5 for b, and you plug in those values into the function, what you just computed with the average rate of change is the slope. 2.5 is the slope of this line. This line has a name. It's called the secant line. Okay. So the slope of that secant line is 2.5. Okay. So that's where we've come from. That's section 2.1 in computing the average rate of change. So that's the first part of section 2.1. Okay. What we did in section 1.8 is we looked at what were called limits. limits. So say the limit as x goes to a of f of x. Okay. So what we're going to need from limits, okay, is to compute our delta x value, or what the book is going to call h. We want to see what happens to this function if we make our spacing smaller and smaller. So if we make it 0.1 and increase the time until you see the 1 and the 1.5. Okay. Now, look at what's going on. We want to look at the value 1. So it's decreased to 0.1. So I've decreased the time spacing. I have increased, let's increase the plot time. Okay. Now take a look at what's going on here according to this table, right? So if you start to make the h value smaller, you start to make the h value smaller, in this case h is equal to 0.1. And you look at the average rate of change of this function from x is equal to 1 to x is equal to 1 plus h, which in this case is 1.1. Right? The average rate of change of this function from 1 to 1.1 is going to be 2.1. So according to the table over there, the function evaluated at 1.1 minus the function evaluated at 1 over 1.1 minus 1. This is what we are calling our h value. This answer will be 2.1. Okay. So notice what was the same in each of these problems. When h in the previous problem was 0.5, the number 1 stayed the same. The number 1 stayed the same. The only thing that changed was the 1 plus h value. Okay. The only thing that changed was the 1 plus h value. So this example should lead us to what we want to talk about, the instantaneous rate of change, the instantaneous rate of change of the function f of x at a given value of x is equal to a. This has a name, right? Is called the derivative of the function f of x at x is equal to a. So the instantaneous rate of change and the derivative, these are the same thing. But what is this derivative? The derivative of the function f of x at x equal to a. This long thing, okay, has a formula. It's called the limit as h goes to 0, the function evaluated at a plus h minus the function evaluated at a divided by h. So if you compare to the example above, here we can see that this is of the form f of 1 plus 0.1 minus the function evaluated at 1 divided by 0.1. 0.1 is our h. The 1 is the a value. Here's your h value again. So, and 1 is your a value. So I think if you look at this formula here, right here in the box, you will see that this is just the average rate of change from x is equal to a plus h to x is equal to a. And then we've thrown on a limit in front, and that will be what we're going to call the derivative. Okay. Rather than writing this long expression, the derivative of the function at x is equal to a, rather than writing that, and rather than writing all this limit a lot, we give a notation. There's a notation for this answer. We're going to call it f with this little prime of a, and this is pronounced f prime of A. Okay, so let's take a look at an example here. Okay, let's see if we can kind of guess. So for the function f of x is equal to x squared, and our particular value of x is equal to a is equal to 1. Okay, so that means that we are really going to be focused in a table of values on the value x is equal to 1. Okay, now we know what f prime of 1 is. This is the derivative of the function f of x at the value x is equal to 1. This has a meaning. It's the limit as h goes to 0 of the function evaluated at 1 plus h minus the function evaluated at 1 divided by h. Okay. Now let's see if we can take a guess here at the values. When you do h, when you pick a particular h value, in this case from the table I have 0.1. Okay. The average rate of change of the function f of the function from f of 1 plus h minus f of 1 divided by h. That's what we're seeing in this column right here. When h is equal to 0.1, my average rate of change is about 2.1. So let's see what we can, if we can guess what this limit is going to be, just using the computer to do a bunch of values. We need to do a limit, so we need to make this value smaller. Let's make it 0.2. 0.2. Let's increase our time. Whoops, actually it doesn't look like I can get to, okay, 0.2, 0.78. I need to change something in the code, but we don't need to do that now. So let's take a look here. Here's our function evaluated at, let's see, 0.05. Does that get me there? Okay, well, we'll just take a look here. I think what we can see is that these values at 1, the next value at 1.05, so when we're about 0.05 for our value of h, it looks like our average rate of change is going to be close to 2. In this case, it's going to be around, about 2.0 something. Okay? So I have a guess that if I went smaller, then I would get closer and closer to 2. And that's exactly what we're going to see. Let's compute this limit out. F prime of 1 is equal to the limit as h goes to 0. The function evaluated at 1 plus h, because our function is x squared, we're going to get 1 plus h squared minus the function evaluated at 1 is 1 squared over h. Okay. We don't pick a particular value of h, we leave h as a variable. Okay, and we're going to see what happens when we try to compute this limit. This is a good mix of algebra skills and whatever, so expanding this out, 1 plus h minus 1 squared is 1 over h. Just doing some algebra here. The limit as h goes to 0. Expanding this out by doing whatever you guys call foiling, I call distributing. 1 times 1 is 1 plus 2h plus h squared minus 1 over h. The 1's cancel out. That will often happen. Limit as h goes to 0. There's an h that I can factor out, 2 plus h. Just working on my algebra skills here. These h's cancel out, and you're left with the limit as h goes to 0 of 2 plus h. And as h gets really small, this limit becomes 2. Okay? So we have shown in this particular example that f prime of 1 is equal to 2. This is pronounced the derivative. The derivative of the function f of x is equal to x squared at the value x is equal to 1. Or you can say that it is the instantaneous rate of change of the function f of x at x is equal to 1. Those are synonymous. So in the next video we will maybe look at doing some more of these limit problems and then discussing the meaning of this, what is the meaning. Next video will be what did we just do, the meaning of f prime of 1, or better yet, f prime of a for any a. So we'll look at that in the next video.